Hey guys, it's Edward. Today, I'm going to show you an example of how I apply my problem-solving systems to an actual coding interview. If you did not watch my last video, I explained how I developed the system I use, the intuition behind it, and why it works fairly well for me. While many of you have your own problem-solving heuristics and tricks, I'm simply going to show you how I think about my own in this video. For all intents and purposes, I won't be focused on writing the code. Rather, because the systems are agnostic to any programming language, I'll be demonstrating my thought process and everything up to before putting code to paper. Consider this an addendum to my previous video. I'll be clarifying each of these steps using a toy example. As a refresher, I'll be putting my flowcharts on the screen. Pause the video if you need to take a read. My problem solving looks like this. 1. Look at the characteristics I see in the problem. Can I combine a sufficient number of these characteristics and match them to a known data structure or algorithm? 2. Let me generate a few examples. What are the patterns generated from the examples? What will the algorithm approximately look like? 3. Look at every substep of the algorithm. For every substep, go back to step 1 with the question, how can I optimize this substep? And here's my efficiency chart. Order 2 to the n to 3 to the n and so on is usually reserved for NP-hard problems or permutations. Order n squared or n cubed is reserved for recursion, generating subsets, or some kind of nested loops. Order n log n is required for sorting and heaps. Order n is for iteration, pointers, sliding windows, and common array operations. Order log n is reserved for binary searches or exponentially sized search steps. And finally, we arrive at order 1, which is hash maps or indices of an array. Now that we've gone over the charts, we're going to actually see how we can apply them to an actual problem. So with that, welcome to the coding interview. You suck. Now, this is a fairly common problem that I ask, and you've probably seen some variation of it in mock coding interviews. But again, the purpose of this is actually to show you how each of these steps work and why they work. The problem is as follows. Suppose we have a meeting room at a university. Students are requesting a bunch of these meeting rooms around the clock. Find the maximum number of meeting rooms we need to support. For the purposes of this problem, we will assume that the time indices are all integers. We won't bother with longs or millisecond conversions. You can assume that the data is unordered. I'll pause the video here so you can solve the problem on your own first. So, let's pull up the first step. 1. Look at the characteristics I see in the problem. Does this match a known data structure or algorithm? Well, if you've gone through my study guide, then you'll recognize this as a type of scheduling problem. And most of the time, these scheduling problems can be solved with heaps, where we group the intervals in order of time. We start off by having 2 heaps, one where the room is being booked, and one where the room is being released. If the values at the front of the heap are the same, we will discard both values and move on. Otherwise, we will take and discard the smallest value between the 2 heaps. If we took from the open heap, we will increment the total number of open rooms currently by 1. Otherwise, we will decrease the value by 1 to represent the room being vacated and keep the running total. This running total represents the current number of rooms that are open, and as we iterate, we will keep track of the maximum value. We will iterate until we've gone through all the room openings. Then, every single request after that is just a closing of a room, which means the total number of rooms at the following indices must be smaller. This algorithm runs in order n log n time for the sorting and order n for the iteration. So, our algorithm comes out to order n log n in runtime. The space complexity is order n space, because we must iterate through every single interval. Now, let's go to the second step. Let's generate a few examples. What are the patterns generated from the examples? Well, because we've already recognized that this is a scheduling type problem, we don't necessarily need to do this step. But let's suppose I'm in a situation where I don't recognize that I can use this as scheduling or I can use heaps. Well then, how do I generate examples in order to gain this intuition? If I were to draw a dummy example, then we can see we're almost forced to order them by time. Now, for the sake of completeness, I would also generate an example that has every possible case. For any 2 given intervals, there are only 3 cases. 1. The set of intervals overlap. 2. The set of intervals do not overlap. And 3. The set of intervals touch on the edge. We will not consider intervals of 0 duration, as we will consider that as an invalid parameter. A room shouldn't be booked and released within the same hour. However, this is a good question to ask in an actual interview if this should be treated. The people who are more conservative and more prone to rushing might actually want to perform this example step first to prove that the characteristics that you've identified in the problem are actually relevant, and also to bulletproof your design and prove that it works. Now we move on to step 3. Let's look at every substep of the algorithm. For every substep, let's go back to step 1 with this question: how can I optimize this substep? Now, this is where our efficiency chart becomes relevant. Remember that as we go down the list, our algorithm improves, but we are only limited to the algorithms to a particular line or below that. In our particular question, we have to ask ourselves if we can improve an order n log n solution, which means that we need to come up with an order n, an order log, or constant lookup time solution. So there are 2 dimensions that we can optimize against: time and space. And yes, you can argue that if you made your code more compact or used less data structures, that it would be an improvement. Those are actually just peanuts though, compared to what is actually important. Let's start with improving the time complexity. Back to the chart we go. Let's look at the characteristics of these problems. Based on the characteristics of the problem, let's eliminate some possibilities. We can rule out order log n and order 1 because we need to iterate through an unstructured data structure. Log n only really works for searching on ordered data structures, and our data is not necessarily ordered. Furthermore, we need to iterate through every single interval in order to check if there is any overlap. Therefore, we are forced to run our algorithm in order n at least. So, can we iterate through these intervals a finite number of times without having to sort it beforehand? What is the order in which we iterate? Do we need to skip other intervals? Do we need to go in order? On some level, we must be able to traverse through a timeline. After all, going from index t equals 8 to t equals 1 does not do anything for us, but really just gives us random intervals. To see if they overlap, we'd have to compare them to every other interval we found, leading us to an order n squared solution. If we go from t equals 1 to t equals 2, then we know that we will have encountered every meeting room open request and close request along the way, so we won't miss a beat. The value at a time index is reliant on the value found at the previous time index. Or, more concretely, the number of rooms open at time of t is equal to the number of rooms open at t minus 1 plus the number of rooms requested at time t minus the number of rooms vacated at time t. Every element gives us 2 things: a start and a stop time. So, can we simply create a timeline of the earliest and latest element? And within that timeline, we only mark the times when we open and the times that we close. Well, this is starting to sound like an array traversal from index 0 to index x, where x is some number. So, I have an array traversal as probably my only pattern that I can use. So then let's move on to the second step. Let me generate some examples, because at this point, I need to know how to populate this array. As I said before, the only values that we really care about is when the intervals open and close. So when a room is requested, we would consider that a +1 to the value, and when a room is vacated, we would subtract a -1 to represent the net number of rooms requested. As we iterate through the array, we add the number in the array to represent the net number of meeting rooms requested. We've kept a running total of rooms that are required from 0 to t minus 1. Then, at time t, we add the net number of rooms required, per our formula. Therefore, our runtime runs in order n, but our space is order x, where x is the highest time index asked of us in the log. So, let's look at our 2 solutions. The very first solution we came up with, we'll call this the naive solution, because it runs in order n log n time complexity, but order n space. Our more optimal solution runs in order n of time, but runs in order x of space, where x is the highest index requested. This is our trade-off considerations, and you can make the case for either one of these. But our more optimal solution wins if the number of time interval is larger than the time window we're looking at for meeting rooms. And in an actual interview, it's important that you actually go ahead and justify every single one of your answers. No matter if you think that the algorithm performs better or worse overall, it's actually really important that you understand and acknowledge when other algorithms and other possibilities work better. Every algorithm has its time and place, no pun intended, and it's really important to acknowledge that to show that you fully thought about what you're doing. I hope this video was helpful and illustrates how my systems work and why I think they were useful. If you like this video, please like and subscribe, and I'll see you all in the next one.